So before we went to break, we talked about why Phoenix Controls made a very specific decision years and years ago that we were not going to measure airflow through our control devices all those years ago. So the question hopefully that occurred to you after that is, well, if we're not measuring flow through the valves, how exactly are we controlling airflow through the valves, right? So the acronym we like you to remember when we talk about how the flow metering approach works is PAINTS. So the valves are mechanically pressure independent. And that's an important feature. We'd like to say mechanically pressure independent because it's true and it differentiates us from other solutions. Okay, we'll talk about how that works in just a bit. The accuracy, we're able to maintain plus or minus 5% of the control signal throughout the full range of the valve's airflow. So that means if we're commanding 1,000 CFM from the valve, we are going to be within 5% of 1,000 CFM. If we're commanding 200 CFM from that same valve, we will be within 5% of 200. So that margin of error, plus or minus 5%, is based on the command signal to the valve. It's not a fixed value, okay? Because we're not measuring flow, the valve is inlet and exit insensitive, meaning the design of the ductwork does not affect the airflow of the valve. There is no scheduled maintenance required on the valve. We can do a up to 20-to-1 turn down ratio. So on our single 10-inch medium pressure valve with a standard valve body, we rate that valve accurate within 5% from 1,000 CFM down to 50 CFM. And that's our greatest turn down, 20-to-1. Okay. Overall system stability, the pressure independent nature of the valve controller provides an overall system stability. We can order valves with corrosion resistant protective materials for exposure to chemical elements in the cabinets. And mechanically, our valves are reliable and simple, so there's not a lot to fail on them as a result. So we say this groan-inducing statement, a successful salesperson paints a picture of how the valve works. All right? So paints. Now, particular product specifications that stand out for a Phoenix valve. A response time of less than 1 second to changing control signal. Our Solaris valves can respond in less than 1 second to a change in control signal. An accurate control range up to 20-to-1. Accuracy plus or minus 5% of signal. Less than 5% overshoot, so we don't overshoot and then stabilize. We go to a position and we stop there. And inter-system stability, this applies to all Phoenix valves. Mechanically, we respond to changes in duct pressure in less than 1 second. Okay. So here's a picture of a Phoenix valve. This is an older valve. It's one of our old analog valves, to be honest. I got to get a better picture. But you can see the shape of the valve. The air moves in this direction through the valve from left to right as the picture is shown. So this side of the valve is the venturi, and then we have a conical shaped diffuser coming out of it. There's been one valve body design change in the 40 years that we have had the Phoenix valve. Okay, the early Phoenix valve had a hourglass shape, that venturi shape on both the inlet and exit side of the valve. In the early 1990s, we changed the shape of the valve diffuser to this conical shape, and that provided two benefits. It gave us a slightly greater turn down ratio, and it reduced the noise generated by air moving through the valve. Okay, so we call this the XL2 valve body. You'll probably never hear that again after you leave this class, but that's the name of the physical valve body itself. We don't use it as a brand name in the field. It just means that it's this second generation of the design of the valve. Okay?
Is that the same across all three?
Every single valve we sell is this same mechanical valve body. So it doesn't matter whether we sell it as a constant volume device, which we can be locked into a specific airflow, whether it's sold as a tiered control, which can be controlled by others, whether it's Solaris, Traxel, or Theris, they all get the XL2 valve body. So mechanically, and this is an important point, it's a great question, mechanically, every single Phoenix valve is the same. It's designed the same. Every 12-inch valve is designed the same. Every 10-inch diameter valve is designed the same. There are differences in controls, so the controller card we mount on it, and actuation for the different applications. But the mechanical design of the valve does not change. There are things that can change certain components of the valve, whether it's going to be mounted horizontally or vertically, whether it's a low pressure range or a medium pressure range. We'll talk about those things. But the mechanical design of the valve is consistent across all product lines. Okay? That's why every single Phoenix valve has the benefit of that less than 1 second speed of response to changes in duct pressure.
What did you say besides noise was the benefit of a conical shape?
It gave us a slightly greater turn down ratio to get to that 20-to-1 turn down ratio. We could go a little lower with the flow. So hopefully you're asking yourself, if you don't already know, how is it that we're able to control if we're not measuring the flow? And the way we like to explain it is if you can stabilize the pressure in a system, in a closed system, then controlling flow is very easy. Because all you have to do is change your control device position. So if we were somehow able to maintain a constant pressure through a system, say 1 inch of pressure, then controlling the airflow through that system would be very easy. Because all we would have to do is measure the flow in the duct 1 time and mark the position of our control device at that airflow. So in the example here, and this is a theoretical example, we all know you can't maintain a constant pressure in a duct. There's no system that can respond fast enough to all the changes. But if we were able to, if we could maintain constant pressure, it would be very easy to do. Measure the flow and mark that position. Say position 1 equals 50 CFM. And continue to take additional measurements. Position 2 equals 200 CFM. Position 3 equals 1,000 CFM. Take as many measurements as you want to get an accurate picture of the airflow design of that space. As long as the pressure is stabilized, we no longer have to measure the airflow once we have that characterization of the system. If it's 1 inch of pressure, then to get 50 CFM, we just have to go back to that first position. So if the pressure is stabilized, your control device position equals a specific airflow. Does everyone agree with that statement? Does anyone disagree with that statement? Because that's an important part of how we work. So if you disagree, let's talk about it now.
So how do you make it pressure independent?
That's the great question, right? So the way we do it is we have this spring and cone assembly. Okay? And this is the secret sauce that makes everything work. I've got a cutaway version of a valve here, and you can see inside this cutaway of this cone, there's a spring in there. So the cone is an obstruction in the airstream. If you looked at a Phoenix valve face on, you're mostly going to see the cone inside of the venturi and just a little space around the edges for it. Well, an obstruction in any flow is going to cause a pressure drop. As that pressure drop changes, the tensions in the spring are designed to respond to that change in pressure to expand or contract the position of that cone further into or out of the venturi, further into or out of the restriction of the valve. And if you looked at a Phoenix valve spring, we'll see some when we go on the factory floor for the tour. The Phoenix valve spring, there's 13 different spacings in each spring. And they're not like a mattress spring where each spacing is an equidistant value. They all have a different pressure factor built into them, which gives us a broad range of differential pressures we support. So that spring, the tensions in that spring allow us to compensate for the change in pressure in each valve across a broad range of differential pressures. And I'm going to put it up here on the board. There's 2 types of valves, 2 types of differential pressures. A medium pressure valve The spring is designed to compensate for a differential pressure. Get a different marker. That seems to be a bit used up. Okay, a differential pressure between 0.6 and 3 inches of water, 150 to 750 pascals. Anywhere in that range, the spring that's inside that cone is going to either compress or expand to a position in the venturi that is going to give us the exact same airflow at that actuator position, plus or minus 5%. We also sell a version called a low pressure valve. And the differential pressure range on that is between 0.3 and 3 inches of water, or 75 and 750 pascals. What do you suppose the difference is between a medium pressure valve and the low pressure valve?
The spring.
It's the spring we put inside of it. The spring has different tensions. It gives us control down to a lower differential pressure. Yes?
What's the pressure range on the low valve? Is it 0.3 to 3?
0.3 to 3 inches. Yes?
Dumb question, Rob. Why not make them all low pressure?
That's a great question. That's not a dumb question. The reason why is you can only get so much airflow through an empty duct at 0.3 inches.
Yeah. Okay.
So you have a lower maximum flow with a low pressure valve than you do with a medium pressure valve. So to give you an example, if you take a 12-inch diameter valve body, a medium pressure valve goes to 1,500 CFM at the maximum flow, and a low pressure valve will only go to 1,050 CFM as its maximum flow. So as a consequence, with low pressure valves, you have to order a larger diameter, which costs more money. But there are sites that will order all low pressure valves in the building because they want the benefit of being able to run lower static from the fans, and they're willing to pay more upfront to do that.
They're probably quieter.
They can be, but it depends on the flow. We have a whole range of documentation on each valve type, its airflow, and the decibel rating for each at different pressures and different flows. So the noise generated depends on the valve diameter, depends on whether it's medium-low pressure, it depends on whether it's at 1 inch of pressure or 3 inches of pressure, and the airflow you're achieving at those. So we have tables of valve sound ratings, which we can share with you. Okay? So the spring that's inside there, that's the secret sauce that makes everything work. If that spring is not designed properly, we cannot meter the flow. So fortunately, that spring is the most heavily engineered piece of the whole valve, even though it's also the simplest, because it's just a stainless, well, it's actually a higher grade than stainless steel. It's a steel spring. Okay. And what happens, as I mentioned, as the pressure in the duct changes, notice my actuator arm is not going to move in this example, but my spring and cone are going to expand or contract as the pressure in the duct changes to compensate for that change in pressure. So when the pressure's lower, the spring expands, there's more space for the air to move through the valve at a lower pressure. So you get about the same volume. If the pressure increases, the spring contracts, it pulls the cone further inside the venturi, so it's a higher velocity of air moving through the valve, but you have less area for the air to move through. So you're compensating for that change in pressure by varying the area that the air can move through in the venturi. And you end up with roughly the same flow, plus or minus 5%. That's where our plus or minus 5% comes from our differential pressure range. We characterize the valves at 1 inch of differential pressure, and if you have 1 inch of differential pressure through that valve, your accuracy should be dead on. There should be no margin. The plus or minus 5% comes from the difference at different positions for 0.6 to 3 inches of pressure across that valve, if it's a medium pressure valve, or 0.3 to 3 inches of pressure across that valve if it's a low pressure valve. But the spring is the special sauce that makes it all work. Now, because that spring is so critical to the functionality of the valve, let me tell you a little bit about the testing that goes into the manufacture of the springs. We import the steel for the springs from one supplier. And when we get a new batch of wire in to make new springs, we create test batches of springs from that wire. When you take the factory floor tour today, you're going to see our mechanical engineering lab. And in there, you will see our test tables for the springs. There's 4 or 5 test tables in there, and each test table has about a dozen springs on it. So what we do is we make test batches of the springs, different sizes, different types of springs. We put them on those test tables, and then we will fully compress them and fully release them. 24 hours a day, 7 days a week, while a counter counts the number of cycles. And we stop when we get to 1 million cycles. Then our mechanical engineers will then take those springs off the test bench and measure the tolerances of the springs to make sure nothing has changed or deformed over that life cycle test that simulates over 20 years of usage in the field. If those test springs pass the testing, then we use that one batch of wire to make all of our valve springs until it's gone, and we do the process all over again with the next batch of wire. So because of the quality of the materials, because of the testing we do on the steel, and because of the simplicity of the design, it's just a spring that's being compressed back and forward, that is the least likely component to fail on any Phoenix valve. I have gone to sites. I'll give you an example. I went to do a training at Wake Forest University in Winston-Salem, North Carolina. Okay? They had valves in there so old that I didn't even know the control system that was on them. I got there, and I was there to train on the old analog control system, and I had a pretty good familiarity with the analog control system. They're sending me there to train on it. So we do the classroom training, and then we go out into the field on the last day. We go out in the field on the last day, I take the cover off the valve, and there's a controller board I've never seen in my life there. I take a picture of it, call our head of product support. I said, I'm sending you a picture, John. Tell me what this is. He goes, oh, that's the telephone jack analog controls. I said, what is that? He said, well, our early years, we had basically telephone wire between the valves, and that's the control board that we used. I said, okay, that's interesting. Can you send me a pinout so I know what's what? He says, I'll send you something. I tell you that story because we also had an air balancer with us, okay? And they wanted to test the valves in the room. And when we went into this lab, once I figured out the pinouts and everything, we did some testing in the room. And so this was building at least 25 years old at this point, because at that time it had been 25 years since we sold the telephone jack controllers. And we were within about 6 to 7% on the air balancer's reading on every valve he tested. Okay? And I'm going to say that extra 2% was his instrument, not our valve. Because you can't disprove that, because he has a margin of error, we have a margin of error, you add them together, that's the true margin of error, right? So I'm not saying every valve is going to run for 30 years and not have to be maintained, but I've seen it. I've seen it in real buildings, in real labs, okay?
How many springs did you say per batch?
Oh, I don't know how many springs. George, when he comes in later, you ask him, he'll tell you how many springs you make from each batch. For the test springs, we do, like, each table has a dozen test springs on it. But then I don't know how many springs we make off of one batch of wire. But
on exhaust application,
yes.
in an OR, where does your sheet length end up?
Goes right through the valve. The velocities through this valve are so high that you might get a little bit of buildup, like here on the center of the cone. But as long as it's not enough to affect the weight of the cone, those things are remarkably clean, because it hits this material and slides right off because of the high velocities.
So at 0.3 inches, what is that velocity?
It depends on the diameter of the valve.
Shouldn't. 0.3
Yep.
across that.
Across the valve, yep.
Should be the same no matter what size valve it is, right?
No, because some valves you'll have 0.3 at different positions with different diameters. You know, depending on if the static is 0.3, it'll be the same differential pressure across the valves. But 0.3 in static is not going to be enough to get you your 0.3 differential pressure across the valve. You need more than that. Yes?
Are there any applications that start to impact how well the cone slides on that rod?
There's one application I know of. It was at Wake Forest. They do smoking testing in chemical fume hoods, and the tar and nicotine from the smoke actually gums up the inside of the valve. So once a year they take them out of the ceiling and they pressure wash them to get all that stuff off of there and then put it back up there. But as long as it's not something that's going to adhere to the valve body or adhere to the cone, then it's not going to affect the flow. What could affect the flow is if the weight of this changes. So in there, they were getting such a buildup of materials on the cone that it was actually changing the weight of the cone for control, and that was affecting the flows. The other thing is, you'll see in our videos, like you could have paper or other obstructions in here. As long as the cone can move freely, and as long as you have your differential pressure range, you'll still get your airflow. Whereas if you had like one piece of paper across a vortex shedder or a pressure transducer, that's going to affect your control. This is not affected by any debris. As long as this cone can move freely, there's nothing in between the cone and the side of the valve, and as long as you can get your pressure drop across it, we maintain our airflow. Okay. So this solution, this mechanical pressure independence, means if you order a constant volume Phoenix valve, you don't get any electronics or actuation on it at all. You get a mechanical device. So there are certain applications where a constant volume valve is the right solution. Toilet exhaust, cabinet exhaust, those types of applications. You can order a Phoenix valve, it's a constant volume valve, you're going to get a valve that is entirely mechanical. We put it on our test station, we adjust the actuator arm until we get the flow that you order, we lock that into position with a set screw, and we ship it to you. No actuator, no DDC controller, entirely a mechanical solution. And as long as you have your differential pressure range across there, you'll be within 5% of whatever flow you've ordered. So when it comes to a constant volume solution, by far the most cost-effective solution is a Phoenix constant volume valve because it's a mechanical solution. Okay? Now, for a VAV control solution, what we do is we move that whole spring and cone assembly further in or further out of the center of the venturi. We have an actuator tied into the actuator arm that's connected to that spring and cone. And as we want to increase the airflow, we drive that actuator to push the whole spring and cone assembly further out from the center of the venturi to give us a higher airflow. So what we're actually measuring in the field is the position of that actuator arm. And this is a picture of what that looks like mechanically on your VAV valves. This is an actuator here. This is a high-speed electric actuator. It's tied to the actuator arm that penetrates the valve body and is connected to that spring and cone assembly. That's the shaft that controls the spring and cone. Well, that turns on a shaft that's tied to a coupler. The coupler is attached to a device that we call the VPOT. And VPOT stands for valve potentiometer. It's a wire-wound, 90-degree turn, 10K ohm potentiometer. What that means is it goes from 0 resistance to 10,000 ohms resistance in 90 degrees of turn. Why is that so sensitive? Because a very small change in the position of the actuator is a very large change in airflow through our valves. The actuator itself only travels about 2.5 inches from fully closed to fully open. In that distance, you could go a range from 50 to 1,000 CFM. So we want that signal that represents the position of the actuator arm to be very sensitive to changes in position. So what we do is there's 3 wires coming off of that VPOT. That's it right there. Normally there's a protective sheet metal cover over the circuitry. But that VPOT has a ground signal, has a control signal, and a reference voltage. So we send a reference voltage through the circuit. As that actuator arm extends and retracts, the actuator pivots on this shaft, which turns the potentiometer and changes the signal, the feedback signal, to our controller card. So here at the factory, we measure 2 things on every valve on our test stations. we measure the position of the actuator arm and the airflow through the valve at that position. And we create a flow table that you'll hear called the valve curve. You hear the term valve curve. We're talking about a 48 position flow table that has the VPOT feedback and the measured airflow at that position stored in the memory of that controller card. So that valve controller card and that physical valve body are one control device. If you separate them when it leaves the factory, you affect the accuracy of the control. So your technicians are taught if they change a damaged controller card, they have to acquire the factory table to put into the replacement card so that we can accurately report the flow for that physical valve. And every single valve gets its individual characterization because every single valve is slightly unique in their flow table. No two valves have the exact same flow table because, as you'll see when you go to the factory floor, these devices are hand assembled. We don't have any robots on the factory floor putting these valves together. I don't even know if you could do it that way because of the way that the valves are manufactured. So it's human beings attaching that coupler and tightening those screws. And when I tighten the screw on one valve, it might have a slightly different starting position than the next valve. So each valve gets its own individual characterization as the last step in the manufacturing process. And you'll see that this afternoon. I've got a video that I'm going to show you in just a little bit that talks about it as well. So what we do, if we need to increase the airflow, we use the actuator to drive that spring and cone further out from the center of the venturi, and that gives us a variation in airflow. So with our Solaris valves, that actuator is a 1 second actuator, fully open to fully closed in 1 second. That gives us our fast respond to change in command. So all the valves have the mechanical pressure independence where we respond to change in pressure in less than 1 second mechanically. The Solaris valves, we can go to a new airflow position in less than 1 second. The Traxel and Theris valves work on the same principle, but they have a standard speed actuator that goes fully open and fully closed in about 60 seconds. Because the applications where we would use those in those environments, they don't require that 1 second speed of response. Nothing changes that fast in an open bench lab or in a surgical suite that you need that actuation. Okay. So what gets generated is this valve curve. And I need to update this slide. We take almost 200 data points. We average them down to 48 positions. And those get downloaded into the memory of the controller card. We also put a label on the inside of the controller card cover which shows 8 of those 48 positions. Now, we used to show 8 of those 48 positions. Now we put some coefficients in there that can be used with our software to generate the table. And I'll tell you why we made that change, okay? Our old analog valves that we sold for years were controlled by 0 to 10 volt DC control signals. And the analog controller cards had no digital controls on them at all. There was no processor. It was all strictly electrical circuits. Well, customers eventually wanted to upgrade those to digital controls so they can control temperature, they can monitor their spaces, pull everything into their BMS system easier. And we have an upgrade solution we're going to talk about later in the week. And part of that upgrade solution is to take that controller card label with the 8 positions and convert it into a digital table that we download to the memory of the replacement card. So you might say, well, Rob, why do we want to go away from that? Well, certain competitors, who we'll talk about later in the week, were selling approved upgrade kits to Phoenix valves. That's how they marketed them, approved upgrade kits. They didn't say who approved them. We didn't approve them. But they were selling them, and what they would do is they would take their own digital controller, they take our analog controller off, they put their own digital controller, and then they would use this information to try to tune their controls. Now, even with this information, it doesn't work very well because they generally end up mixing pressure-independent control with pressure-dependent control because that's what they're used to. Like they'll put like an orifice ring on the on the valve and try to control based off of that. It's not a very good solution at all. And we have data to show that. We have sites that did that approved upgrade, and then 6 months later came back to us and said, hey, can you undo this and put Phoenix digital controls? And we said, sure, we can do that for you, no problem. But to make it more difficult for them to attempt this, we've taken the 8 data points off of the label. There are coefficients that you can use our software to recreate the curve, but you can't just look at that and use other software to recreate the flow table. Okay, so we did that to make it a little less likely that someone is going to try that. The other thing that I will point out to you on this label, it has an altitude listed here. So here at Phoenix Controls, we are basically at sea level, 40 or 50 feet above sea level. The air density here is different than the air density in Albuquerque and Denver and any other place I can think of that has a very high elevation. So when you are ordering Phoenix valves, one of the things we ask you to put into the software is the elevation of the building that it's going to be installed in. Because we can compensate for changes in air density. When we measure the flow here at the factory, we compensate for the air density about every 1,000 feet of elevation. Okay, so that is an important part of the ordering process, telling us the elevation of the building that the valves will be installed at.
How specific would you need to be?
Yeah, a couple hundred feet. We go every 1,000 feet makes a difference. So, you know, if it's 1,500 feet and you say it's 1,400 feet, that's not going to matter. So yeah, just go to Google and whatever it says on Google is the elevation and use that. You don't need anything precision. Yes?
Is that flow curve like both directions, all the way up and then back down?
No, it's consistent. So it's just one value. So this is a position and this is an airflow. So it doesn't matter whether I'm going up with the flow or down with the flow. I'm going to be somewhere on this range at that particular position, and it will correspond to a particular airflow. So I have a video, and I'm going to show it to you here. Now, this video is available on our YouTube site. You may not have known we have a YouTube site, but the reason why I show this video in class is so you know about it, and you can share it with customers who might be interested in how our systems work. So this video is going to talk about the valve characterization process. Now, you're going to see this later today when we take the factory tour. You're going to see how the valves are individually characterized. This is simple industrial. That's not our product. I love how YouTube puts ads on our ads. Okay, this is our presentation. So this is how the valves are characterized.
My name is Dave Boisvert, and I'm the engineering manager at Phoenix Controls, in charge of all the engineering functions, and I've been here about 18 years. Valve characterization is the process that Phoenix Controls uses to verify every single valve that's built throughout the manufacturing process. We take every valve, we mount it on an air station, and we run it through a rigorous characterization process which verifies that everything and all the tolerances are right where we want them to be, and that guarantees us a plus or minus 5% tolerance on every valve that we ship. As soon as the valve is fully built and fully assembled, it then gets walked to the air stations, and at those air stations it gets connected in the same configuration that it's going to be used in the field. We then connect all the electrical connections and run a full operational test similar to how the customer would operate the valve in the field. At that point, the valve then begins with min and max verifications of flows to make sure that it's actually meeting the full requirements and specifications of the valve. Then we take that valve and we run it all the way through every flow throughout the entire range of that product and verify that the entire product goes through and meets a 5% validation of that flow. Only if the valve passes that test can it then be taken off the air station and put into the final assembly area and shipped. Twice a year, we take every air station in production and engineering, and that amounts to 8 air stations, and we run them through a very rigorous process where we have NIST certified Venturis that are all placed on the air station, and we validate the entire flow of the air station. We also have annual calibrations of every single humidity, temperature, pressure instrument that's on the air station, And in addition to all of that, we have a daily golden valve test. And a golden valve is just a valve that we already know what the flow is. We take that valve and we run it on the air station. And if it doesn't pass that air station that day, the air station will not operate and it will shut down, and an engineer would have to come out and investigate what the situation is. The customer's main benefits from having all of the process done that we do at Phoenix Controls is, number one and most predominant, is safety. We want to make sure that the scientists, that the medical professionals, that all of the people that work in these facilities really have the safest product out there. Secondary to that is energy. We want to make sure that they're saving the most amount of energy because it is extremely costly to run these types of facilities. And the third major benefit is we want to make sure that the product goes out of here the highest quality possible. That's why we spend the additional time to run this test on these air stations to make sure that what we send out is exactly what the customer expects.
Okay, so we do have a YouTube page, we do have a LinkedIn page. I've never seen any activity on our Twitter, so don't go to Twitter to look for activity from Phoenix Controls. Now, one of the things that Dave mentioned in that video is the testing we do on the air stations. So each one of our air stations is an NVLAP accredited measurement laboratory. So it's not just that we use NIST traceable calibration devices, although we do. You see this picture here is of a calibration of our air station. And so twice a year we do a calibration using these Venturi tubes. These Venturi tubes have been independently tested to verify, combine those two words there, independently tested to verify the flow through them at a particular pressure. And there's 6 of those tubes we use to calibrate the air stations. They go from the smallest airflow we produce, 35 CFM, to the largest airflow we produce, 5,000 CFM. Okay. We do that twice a year to make sure the air stations have not changed any of their performance and to recalibrate them. We also do that daily test that David mentioned in the video. And the daily test is using something called the golden valve. And the golden valve is a stainless steel Venturi valve. And all we're looking for in that test, it's the first valve that goes on an air station every day. And all we're looking for when we do that test is that today's results are the same as yesterday's results, are the same as the day before's results, going all the way back to the last semi-annual calibration. That way we know nothing has changed in the measurement capabilities of the test station. If it's consistent from day to day, nothing has drifted, nothing has to be adjusted. If an air station fails that golden valve test, it's taken out of production until an engineer determines why we're getting a different reading today than we did yesterday. Now, all of that is the part of the process of achieving this accreditation, NVLAP. We maintain these test stations to an international standard, ISO 17025. And it's not us who says that. We have an independent third party who comes in and makes sure we meet that standard to achieve the accreditation. So the independent third party is called CESI, the Colorado Engineering Experiment Station. They are an NVLAP lab. They get no financial benefit from Phoenix Controls other than we pay them to come in and test us to see that we're meeting the standard. So they come in every year and audit our processes, our procedures, our test stations, and they take production valves off the floor and bring them back to their facility to test their accuracy. And as long as we meet that yearly audit, we're able to maintain this accreditation, this NVLAP. And what I'd like to do is to show you, because you can share this with your customers, that if you go to the website, if you Google NVLAP, this is a program of NIST. It's the National Institute of Standards and Technology. They manage this program. It's a US government site. And one of the things you'll find there is a directory of accredited laboratories. And we can direct customers who are interested in more information about this here. They can search for us by typing Phoenix in the laboratory name search, and you'll see Phoenix Controls, Acton, Massachusetts, comes up as the only result. And that brings up our accreditization. So it's an annual accreditization, has to be renewed annually. It expires at the end of this month, so we have to renew it before the end of the month for another year. And if you want to look at the scope of what we are accredited for measurement, you can click on this accreditization scope, and you'll see we are accredited to measure accurately those two values we test on each test station. DC voltage, which is the feedback of the VPOT that represents the position of the actuator arm, and volumetric flow, which is the airflow that we measure through the valve. So we do measure airflow through our valves one time here at the factory on NVLAP accredited test stations. We do that because we want to make sure that one time we measure the flow, those test stations are as accurate as they can possibly be. That measurement is as accurate as it can possibly be. You may have an airflow measurement tool that is as accurate as a Phoenix test station if it has also achieved this NVLAP accreditization. But there is no independent measurement of accuracy higher than NVLAP. So no one can credibly say our measurements are more accurate than a Phoenix test station, because this is the highest standard. And that's why we do it. We want our airflow measurements here at the factory to be of the highest standard, because that is the only time we're measuring the flow through our valves. Okay. Some other kind of things to keep in mind with our flow station. If you looked at the shape of that curve, it's a very even change from minimum flow to maximum flow. There's no gaps where you have a large change in signal. Whereas like with a blade damper in a VAV box, you have, a quick opening. You go from 0 to 30% open really fast. And then there's a long, kind of steady change. And then at the top, you have kind of a slow changing as you get close to parallel to the duct. Whereas with the Phoenix solution, it's a steady change all the way through the flows. So you get an equal change. You don't have gaps or places where you respond faster than others within the airflow of the device. Because we're pressure independent, it does not matter the geometry of the ductwork coming into a Phoenix valve or leading out of a Phoenix valve. Okay, so these are pictures from the field. This is a fume hood exhaust valve. You see we put a sticker on here that tells you the direction of the airflow. Tell your mechanical contractors it matters. The sticker has to be pointing in the right direction in the duct. They don't work backwards. Sometimes we see that. But we have a 90-degree turn into the valve and a 45-degree angle coming out of it. It does not affect the accuracy of the flow as long as we have our differential pressure across the valve. Here we've got valves coming directly out of a bank of chemical fume hoods right into a 90-degree turn into the exhaust plenum. Again, does not affect the accuracy of the flow. This one we used to take to design engineering meetings, and we'd say, all right, guys, in this system, where would you measure the airflow? And there'd be a lot of silence typically. And eventually some brave soul would speak up and say, well, I'd put a flow sensor here and hope that it's correct. And we had a sales engineer who always replied, hope is not a control strategy. So because we're pressure independent, mechanically, we don't have to worry about the shape or the design of the duct. As long as we have the pressure drop across the valve, we'll be within 5% of the commanded airflow. Okay. A couple things I like to point out with these pictures. Okay, all these valves are brown colored. You kind of see this reddish brown color. That is for chemical fume hood valves. They've been coated in a protective coating, a baked phenolic coating, to protect the metal from corrosion and exposure to the airstream. That's one of the options when you're ordering a valve. Do you want it coated for protection or do you want uncoated aluminum? Okay. Another thing to notice here, the stickers. The airflow directional sticker. You see this one here is a white sticker and there's text on it. Let me go back one. You kind of see these ones, there's a yellow sticker on there and there's different text on there and different colors because it matters the orientation you order and install the valves. There are 3 orientations for a Phoenix valve: horizontal, vertical upflow, vertical downflow. The valve should never be installed in any other orientation. There's no 45-degree angle Phoenix valve. And if it's ordered horizontally, we test it at the factory horizontally, it should be installed in the building horizontally.
Horizontal, vertical, flow.
Vertical up and vertical down. And we put different color stickers on there. Horizontal valves have a white sticker. You can see that right here, white airflow sticker. Vertical up valves have a yellow sticker. And vertical down valves have a blue sticker. They all have different text on them. If you can read the text without turning your head, the valve's installed properly, because we put the text on there in the proper orientation. If you have to turn your head to read the text on the valve airflow sticker, it has not been installed properly. Why does the orientation of the valve matter? The weight of the cone on the spring. A horizontal valve, there is no weight on the spring. But a vertical valve, gravity is either pulling that spring and cone further into the center of the venturi or pulling it away from the center of the venturi. So we put sometimes different springs depending on whether it's horizontal or vertical. We also characterize them on the test stations if they're going to be horizontal or vertical. So you'll see when we go to the test stations, we have attachments to measure the air horizontally. We have an attachment in the floor that we can pull up a grating on the floor and we can push the air up through a vertical up valve. Or we have an attachment where we can hang a valve off of it and push the air through it vertically down. And that's how we characterize the valve, how you order it. If you install it in a different orientation in the building, our airflow characterization is no longer valid. If you order a horizontal valve and you install it vertically in the building, the airflow will not be accurate to within 5%, because it may have the wrong spring and cone, and because it was not characterized in the orientation that it's installed. So what do you do when that inevitably happens? Well, you have a couple options. You can order whole new valves with the proper orientation. That's pretty pricey. Or you can order something called a field reorientation kit. And with a field reorientation kit, we send you a shaft, spring, and cone assembly, all put together. You take the valve out of the ceiling, you remove the brackets that hold the shaft in place, you take the old spring and cone out of it, you put the new spring and cone into it, you put a new sticker on the side of the valve to indicate that you've changed the spring, you put it back up in the ceiling, and then you get an air balancer to help you field calibrate that valve. Because even with the correct spring and cone, the original factory calibration, or the original factory characterization, I should say, is not going to be accurate. You'll have to adjust that using our software tool. So worst case scenario, you have to do that and field reorient the valve. It's best to try to avoid that by ordering the valves in the proper orientation and making sure that your mechanical contractor installs them in the proper orientation. Okay? Yes, Miles?
What's the tolerance on vertical?
5 degrees. So the orientation is 5 degrees tolerance for horizontal, 5 degrees tolerance for vertical. The good news about that, that's just about the angle you can detect when you're standing on the ground looking up in the ceiling and looking up and say, hey, that looks crooked. If you're sitting here and saying, hey, that looks crooked, it's probably more than 5 degrees. Okay? Yes?
Is there a cost difference between the different orientations?
The orientations, I don't believe there's a cost difference between different orientations. We just want to make sure there'll be a cost difference if you have to do a field reorientation. Yes. Yeah. No. What varies the cost of the valve are the controls, the diameter, whether it's coated or uncoated, whether it's shut off or standard, those types of things. But orientation shouldn't affect the cost. Those cost questions I can answer. Are there other questions? Oh, I don't want that. Hold on. Okay, so I have a video I'm going to show you about this inlet and exit insensitivity and the pressure independent nature of the valves. This is not on our website because it's about 30 years old. So the quality of the video is not what I would say is HD quality. So I apologize for that. It was originally recorded in a format called Betamax. Some of you older fellas might know what that was.
Or superior VH.
It was the superior technology that lost out to superior marketing. That's one of those marketing case studies, right? So yeah, so it was transferred to digital, but there was a quality loss. So I apologize for that, but I want to show it to you anyway because I think it's a valuable demonstration of how it works.
Here we have manifolded 3 valves together and connected them to our test station. This demonstration shows how Phoenix XL valves are inherently stable, even in a manifolded system under constantly changing conditions. To demonstrate inter-system stability, we adjust the top valve's volume to simulate the movement caused by opening or closing a hood sash. Notice that the other valve controller doesn't move, but its cone reacts smoothly and in a stable manner in less than 1 second to the change in duct pressure. This fast response prevents any potential for an inter-system oscillation between the valves. Here we see all 3 valves responding to the change in volume caused by the first valve. Now we will radically change the downstream duct pressure at the top valve. Notice that since actual flow is reduced by the downstream blockage, the top valve opens to increase flow. At the same time, the overall static pressure in the manifold is increased so that the other valve opens to maintain a constant flow.
So that one does a nice demonstration of the pressure independence of the valve. I wish we had a more up-to-date version of that. This other one is going to talk about the inlet and exit insensitivity of the valve. Again, this is a bit older. I wish we had a more up-to-date version. We have a similar version to this, but this one I think is a little bit better for our purposes here.
To demonstrate the complete inlet and exit insensitivity of the XL valve, we have connected a clear cutaway version to our test station. The valve has been commanded to a 500 CFM flow set point. The screen inset shows the actual flow and static pressure in the duct as measured by the test station. First, we bend the ductwork to a 45-degree angle. Next, the duct is bent further to a tight 90-degree angle. As you can see, the measured flow remains virtually constant at 500 CFM. Although not necessarily seen in the field, this tight 180-degree bend definitely shows the valve's complete inlet insensitivity, as does the following tight S-bend. Even this unlikely arch bend does not affect the flow through the valve. Notice that when the flex duct is pinched and severely restricted, and even when part of the duct itself is pushed inside the valve, simulating blockage caused, for example, by lab tissue or a loaded HEPA filter, the flow still remains unchanged.
You know, what we teach the technicians during startup is you work with whoever is managing the fans, and you work with them to establish a static pressure set point that all the valves in the building are satisfied. So that sometimes involves a little bit of trial and error as you raise and lower sashes to make sure you don't get a low flow alarm across a Phoenix valve when that happens. So then that becomes your static set point for the system, whatever will satisfy all the valves in the building. What that can be depends on how the building's designed. I was in a building up in Canada. It was a research building, and the design of the mechanical system was so poor that they lost about an inch of static between the air handlers and the floor of the penthouse. So they couldn't generate enough static for the whole building. I said, you guys gonna fix that? And they said, yep, as soon as the lawsuit is settled, we'll fix it. So. All right, so the benefits of flow metering versus flow measurement for critical environments. Each valve is individually characterized to accurately represent the flow plus or minus 5%. We don't have to worry about the inlet or exit design of our duct system. We have a mechanical pressure independent speed of response of less than 1 second, and we can also have a control response of less than 1 second. And there's no scheduled maintenance required with our Phoenix valves. Okay, you don't have to worry about drift over time. You don't have to worry about cleaning devices. Like the only place I know of is where they do it for those smoking fume hoods where they have to pressure wash them because it changes the weight of the cone. But other than that, I don't know anywhere else where you have to have regular preventative maintenance on your Phoenix system. So we talked about this, the pressure ranges for our valves. A medium pressure valve has a minimum of 0.6 to 3 inches, 150 to 750 pascals. The low pressure valve is 0.3 to 3 inches, so if they need to run it lower static, you have that option. And you also have the option to mix in a building medium pressure valves closer to the fan and low pressure valves further away from the fan. And that gives you more flexibility in the design of the building when you're trying to keep the cost low, but also satisfy the requirements for lower static. You can put the medium pressure valves on 2/3 of the way down the duct, and the last third do low pressure valves to get the benefit of that extra lower pressure range. Okay. We offer shutoff valves, and we sell shutoff valves in 2 different varieties. There's a metal on metal seal. We call that a standard shutoff valve. And then we have a version that has a gasket on the back side of it, designed for decontamination sequences. So what happens when that gasket is drawn against the ridge in the valve, you get very low leakage. The standard shutoff, the metal on metal seal, is for energy efficiency. You want to be able to just shut down the flow for energy efficiency. So you'll get like a 2 to 4 CFM leak through that valve. If you're just doing it for purposes of energy management, it's not a big deal. But if you were using it for like a decontamination sequence, you want to isolate a room from the HVAC system and seal it and pump in, vaporized hydrogen peroxide or some other agent, then you could use a low leakage shutoff if allowed by the code. Codes vary, so check local code. But that has a neoprene Viton gasket on the back side of the valve that gives you a tight seal that will leak less than 0.005 CFM at 5 inches of pressure. So for all intents and purposes, that's a good tight seal for something like that. Okay. And we pressure decay test each shutoff valve, each low leakage shutoff valve that we send you to make sure they match that performance. Okay. So that's for isolation applications. So the advantages of the Phoenix valve: accurate and stable control across a broad range of differential pressures. Our NVLAP accredited test stations we use to characterize the flow of the valves. The widest turn down range of any technology. We have some anti-fouling features built into the valve. I'll show you a video here in a second. But essentially, if any paper debris gets into the valve, the brackets that hold the shaft in place are sharp by design. If you ever handle a Phoenix valve, don't run your finger along the length of the bracket. You will cut yourself. And don't grab it by the bracket either. That's not a good idea. But that's designed, if any paper or light debris gets into the valve body, eventually it's going to shred on that bracket and get pushed through the valve and not foul it. Okay? We have that mechanical pressure independent action that's responding instantaneously to changes in duct pressure. Because of that, we don't worry about the inlet and exit design of the duct. We have the fastest response time both to changes in pressure in the system and to be able to go to a new control flow within 1 second. You can, with our Solaris valves, order them with an optional fail-safe feature. If there's a loss of power, they can drive open or closed. And there's no regularly scheduled maintenance with the Phoenix valves. So all of that
Hi, my name's Ken Crooks. I'm a sales engineer here at Phoenix Controls. I support our sales channel and our customers. When customers come to visit the factory, one of the important things we do is take them out here and show them the red valve demo. It's an operational valve with a clear plexiglass cover on it, so you can witness firsthand the mechanical pressure independence characteristic of the Phoenix valve. Each air station is equipped with a computer and a screen that shows you -5 to +5% accuracy. That's the blue bar at the bottom. There's also a readout of CFM. So in lab-like conditions, NIST traceable devices, we do measure flow at Phoenix Controls, but here at Phoenix Controls, not in our devices in the field. So what we'll do with the red valve is we'll vary pressure. We speed up our fan. We start off though with just 0.3 of an inch pressure drop. And with just that small amount of pressure, the cone is still able to do its job to maintain ±5%. Once we see that, we then ramp up the fan more, go to an inch total pressure. And we'll vary that pressure drop across the valve, showing that cone moving further inside eventually, still maintaining constant flow through the device, ±5%. And then we'll ramp it all the way up to 3 inches pressure drop, our maximum Phoenix valve. And the cone's further seated into the venturi, maintaining ±5% of set point at all times. So when a variable air volume terminal unit is connected to our air station, or VAV box as it's commonly called, they measure flow. They're not mechanically pressure independent like the Phoenix valve. Any change in pressure drop is then a change in flow. It has to measure that change. The controller then has to move the actuator. That takes time. You can lose room pressurization. You can lose fuel containment. There's also inaccuracy with that. When we're done with the pressure drop test, we then take the red valve demo, and with a flexible duct on the inlet side of it, we'll move it all around and simulate some of the real-world conditions we see. Buildings as they're built today, there's just not a lot of room for straight duct runs. And so even with an elbow directly feeding into the valve and directly out of the valve, there's no impact on the valve's performance. With a VAV box, per ASHRAE design guidelines, they need 10 duct diameters of straight duct, 7.5 on the inlet side and 3 on the outlet side, to get as accurate as they can possibly be. That's just not really obtainable in the built environment today. So another important test we do here during the red valve demo is inject lab tissues into the duct stream and watch them get stuck or flow straight through the Phoenix valve, and how it has no impact on the accuracy of the Phoenix valve. The mechanical pressure independence, the cone spring assembly, not affected by any lab tissues being stuck inside. With a VAV box, it takes just one tissue draped across that flow measurement device, and all bets are off. We've seen 30% loss of accuracy from just one tissue. The red valve demonstration shows our customers really what they need with a terminal unit, the safety and savings that come from mechanical pressure independence.
So do we get one of those for free when we signed up?
What, the red valve?
Yeah.
No, but if you bring customers here to the factory for a visit, that's one of the things we're going to show them, is that red valve demo. And we'll let them, put the tissue into the valve and see whether it affects the flow or not, all on their own, and see for themselves how that works. I think the record, we had like 1.5 boxes of tissue someone put in there before they actually believed the valve wasn't going to be affected by it. But eventually they're like, okay, yeah, we believe you.
Throw a handful in there at one time?
You can try.
Does Brian have one in Atlanta or not?
I don't think so, no, only here at the factory. We do, but for demos, we have cutaway valves that you can demonstrate to people, so you can see what's the components of the valve, how it controls, etc. Okay. Yes?
Do you have a video similar to that with direct competitors, like showing side by side the response time and everything else with your valve versus theirs?
We have about a 40-minute video on that, yeah, that we'll make available to everybody. And that's also a demonstration we do live here at the factory. Right across the hall, we have our demo suite. There's some competitive product that we've acquired through various means that we're all perfectly legal, but we can test against them. Okay. All right, so I just want to spend a little bit of time talking about how the valves are constructed, and then we'll talk a little bit about the different product lines, and then we'll break for lunch here. So every single Phoenix Controls valve in the entire world was manufactured for that location, in that room, in that building. When you take the factory tour, you will see in our warehouse, we do not have valves in our warehouse. We build a valve for a specific room on a specific job, And then as soon as that's manufactured and tested, it ships out the very same day. Yes?
What's the lead time on this?
Minimum, what, 2 weeks for a valve?
They're running about 4 to 6 weeks.
4 to 6 weeks? Okay.
Might ask that next week.
Parts are shorter than that. Parts are shorter than that, but for a full valve. And, you know, usually your lead times will be a lot longer than that because you're going to see the construction window going out, you know, 9 months, 12 months, 18 months, whatever it may be. We have folks who work here who are just, their only function is to plan when jobs build and ship. So they meet your requirements to get to your site when they're supposed to be there. But every single Phoenix valve is built according to your specifications for that room in that building. And one of the things we're going to show you here this week is when you order a valve, how you select all the different options that go into the manufacture of that valve. Every single valve has on it a barcode label. That barcode label has the name of the job, has the room where it's supposed to be installed, has a tag number that corresponds to the plans for the building, and has a serial number that identifies it to Phoenix Controls. And why I point that out, a couple different things. You want to talk to your mechanical contractors and make sure they understand that that valve needs to go in that room where that tag says it should go. Our valves are not generic. They have a specific function in a specific place, particularly if you have the Traxel or Theris product. Because with the Traxel and Theris product, we sell those valves in pairs. We call them tracking pairs. You get a supply valve and an exhaust valve together. And the supply valve has the flow table for both the supply valve and the paired exhaust valve. So if you just take a 10-inch exhaust valve and put it in the wrong room, now the supply valve that it's wired to has the wrong flow table in its memory for that physical valve body you installed. Yes?
I'm just trying to wrap my head around this. So you're saying you need a supply valve for every exhaust valve?
For the Traxel and Theris applications, which are the low-speed applications, we sell them in pairs. A supply valve and an associated exhaust valve.
Okay, can you give me an example of what that would look like in use?
So you have a vivarium. You need to control temperature and pressurization. You have a supply valve and an exhaust valve.
Exhaust valve, and that's for the whole room?
For the whole room.
Okay.
We don't use those products with fume hoods.
That's what I was trying to
In a fume hood lab, every valve has its own controller, and they're all separate. We make them together, one solution in software. With the Traxel and Theris products, they're one solution. Those supply and exhaust are paired together because the application doesn't require individual controllers.
Right.
Okay? But it's critical if you order those applications. You know, if I'm installing terminal units or something that's field calibrated, I have a 10-inch box, I just throw it where I need a 10-inch box. I don't worry about what room it's associated with. With our valves, that's not the case, especially with those tracking pair applications. We only have one controller card per pair. It's mounted on the supply valve. It has the flow table for the supply valve and the exhaust valve associated with it. If they don't put the right exhaust valve in that room, the flows are not going to be correct. Okay? Yes?
So if you have one of these supply exhaust pairs,
Yes.
if one of them breaks or needs to be replaced, would you replace both or just one of them?
Well, I mean, when you mean break, is there mechanical failure? Is there electronic failure, actuator failure? Like, the only reason why you'd have to worry about both of them is if the controller card was damaged. Because the controller card has the characterization of the valve in its memory. So when you replaced it, you'd put both flow curves into it instead of just the supply valve. But if something mechanically breaks on one of them, you just fix that on that particular valve. Okay? So when you are ordering valves, you are going to select a room number and a tag number. You're going to enter that as part of your ordering process. And then you're going to select how we're going to manufacture that valve. You're going to create what's called a product catalog number. And that's where this handy chart comes in, the valve ordering guide. Because this will help you figure out the options you need to order a valve. And if you look at all the different options on this chart, there's over 1 million different combinations of how a Phoenix valve can be manufactured, which is why we don't have completed valves in our warehouse. We don't have the space for all of the different combinations. Okay? So the software does kind of walk you through each of these selections, but you probably have seen these up in offices where we do a lot of Phoenix business.